So we start off with the gradient function. Now we've talked a lot about functions so far, and basically so far functions have simply been, oh, how do I get the y value? If I'm looking at a graph, I sub the x value in and I get a y value. Well, the gradient function is when I sub the x value in, I get the slope of the graph. So rather than the y value, how steep it is at a particular point. Okay. It's also known, more commonly called the derivative, and you might have heard of that word before, derivative. So that is our gradient function. Now we can use geometry to find it. That's if we've got some shapes that we recognise, lines and semicircles, and we'll have a look at that. So if it's a line, remember we know a horizontal line has a function equal to a constant. So the gradient function for a horizontal line, well, a horizontal line always has a slope of 0. So it must have a gradient function of 0. Now, if it's a line at an angle, so an oblique line, which we know can be written as mx plus b, well, slope was n. So it would have a gradient function of n. So there's not a lot of work to do there. We know that because of what we know in coordinate geometry. So that's a line. Semicircle, a little bit more involved. We know that the function is the square root of r squared minus x squared. Okay. But there's not a consistent slope, so we're not going to get a constant value for this function. It's going to be some other function. All right, so there's our random point on the curve. Has an x value of x, has a function value of function x. Now, when we talk about slope of a curve, what we're really talking about is the slope of the tangent at that point. So whatever the slope of that tangent is. So let's create it. Things we know. We know that the radius is perpendicular to the tangent. Okay. So we can find the slope of OA. It'll be the function value over the x value. y2 minus y1 over x2 minus x1. So that'll be the slope of OA, which means the slope of the tangent would be the negative reciprocal of that. So we now know the slope of the tangent. So function x is the square root of r squared minus x squared. The gradient function, well, instead of writing function x, I'm substituting in the square root of r squared minus x squared. So that would be a formula for the gradient function of a semicircle. Well, one that's centred at the origin anyway. So minus x on the square root of r squared minus x squared. Of course, if we had to do this for every single shape, it's going to take a long time. So we need to come up with another way. And so to start off with, we're going to estimate it using secants. So let's have a look at quadratic then. So standard quadratic, y equals x squared. There's a particular point, 2, 4. So we know at x equals 2, the function value is 4. Our question is, what is the gradient or the gradient function at that point? So how can I do it? I do it by estimating. I'll choose 2 points, one either side of the point 2, 4. And I'm going to choose mine symmetrically, so I'm going to choose the point 1, 1 and the point 3, 9. Then I'm going to say that, well, I'm going to estimate the slope of my tangent to be the slope of that secant that I've drawn in, the line that goes through, because I can find the slope of that red line. So I end up with a slope of 4. Now, so I think, and at this stage it's an estimate, I think that the derivative or the gradient function at x equals 2 would be approximately 4. Of course, how accurate my answer is going to depend on where I pick my 2 points. I mean, if I'd say I'd chosen B where it is, but I'd put A over here on the left-hand side, and clearly I'm going to get a terrible estimate. So it does depend on that. Now, it actually turns out that is correct. It is 4 at that point. So here's a parabola. Let's generalise it. So any point x and its function value is x squared. I'll pick a point either side. So x minus some value that I'll call h, and on the right hand side x plus some value. And the function value then would be x plus h squared and x minus h squared. And so we could do the same thing. Slope of that secant will be the difference in the y values over the difference in the x values. And that tidies up to be 2x. And that also turns out to be correct. The gradient function for y equals x squared is indeed 2x. Now, the reason this works is because I chose it symmetrically. And for quadratics, it'll always work if you do it symmetrically. So that's why when I generalised it and did it symmetrically, it worked perfectly and I got the correct answer of 2x. Let's have a look at a hyperbola and see what happens. So the function value is 1 on x. There's my point to a half. So if I go symmetrically either side that, we'd have 1, 1 and 3, 1/3. Okay, let's work out the slope of that. It's negative 1/3. Well, so I'm saying, well, it's going to be approximately negative 1/3. That's not correct. That isn't actually what the value is. The value is actually negative 1/4. So choosing symmetrically on the hyperbola doesn't work. Now, the other thing that's important, the graph also needs to be continuous between the two chosen points. Imagine on this hyperbola, I chose one on the right-hand branch and I chose another point on the left-hand branch. So if I used BC right there, well, I won't bother working it out, but as I say, you see that there's no way that's a good approximation for the slope of the tangent at x equals 2. Okay. So if you have got a good graph, possibly it's better. I mean, okay, yep, the semicircle we can work out a formula, the line we've got a formula, and the parabola we know, well, if we choose it symmetrically, we'll get an exact answer. Any other shape, it's probably just better to draw a tangent in and physically use the estimate of that line itself on the graph. But of course it does require you to have an accurate graph to do that. So that's where we'll stop with today. I mean, we'll obviously later on down the track find better ways of doing it. But at this stage we're just going to be estimating it. So 9A